Okay, today is October the 31st. Happy Halloween. And it's also our 82nd Western Desiderata Extinctionati meeting. And we'll start off with if you have any contacts that you've reached out to. So finally, we're going to have a talk with Derek Jensen in November. So please look out for that. And that's all I have for now. Everyone else kind of fell apart, but that's it.
I have no contacts that have got back to me. I sent some reminder emails, but I have nothing to announce.
Yeah, it's been quiet for me. I haven't really got anything either. Yeah, I've been doing cartoons and stuff. I'll post them when I'm finished. But yeah, I've been trying to write stuff, and I've been pursuing all that kind of angle with into like Britain and stuff, and they seem to be carrying on. They're doing quite well. They're getting quite a good exposure, but I haven't been trying to contact them. I just assume they're way too busy, and they're going to be at COP. So I presume they're just going to wait till after COP. So see what happens then. Yeah. So whatever. Yeah. Um, yeah. So going south is just saying that there was this thing called ICE 911. It's called the the Arctic Ice Project. They changed the name of it, but it's this thing for this woman called Dr. Leslie Fields, and what they've been trying to do is trying to start these geoengineering experiments for glass microspherules. I don't know if you remember that story. There. So yeah, we wrote up a thing together to try and say that to stop them doing this project in Sweden. Sweden seems to be kind of okay with doing geoengineering for some reason. Maybe they've got Becks under their skin or something. But it's really incredible how lame the science is on that. What's they've been thwarted now. They were going to get some money from the EU and I think from Sweden, but the indigenous people have been objecting. Indigenous people, the Sami, they objected to SRM experiments, and in Russia and in America, I think there were 3 objections. So that's kept SRM on the ground. But that microspherular project is really dumb
Sorry, could you
because
explain SRM?
what as solar radiation management. That's David Keith. So we spoke about that on the meeting this morning, on the Eastern meeting, and that's the really dangerous one. That's one backed by Bill Gates, and that's the scary one. But that's basically putting sulfates or sulfuric acid in the stratosphere, dimming the Earth by about 3%. And yeah, it'll almost certainly work, but it's crazy scheme to even think about doing. But they're pushing ahead. It's going to be Plan A very soon, and so yeah. So all the others are silly. The only other ones are marine cloud brightening. That's where you get a ship and you spray water as high as you can into marine clouds to make them denser so they reflect more, increase the albedo, which I think is also freaking stupid because it's like putting, big vacuum cleaner in the sea. You want, you're just hoovering up marine life and shredding it in a liquidizer. And I don't think you can, you can separate marine life in a filter properly, and then you still got to drive this stuff into the air, which is kind of self-defeating. They also that's also risky because the water vapor is one of the most potent greenhouse gases, and this is putting water vapor up into the air. So they have to do it very carefully to make sure that the brightening is offsetting the warming. But it's also crazy ass shit. But Beckwith likes it, and so does the things like Peter Wadhams likes it. But the glass ferrules thing is to get about a 6 micron layer of these glass microspherules. Are a commercial product. They're little glass beads about 6 microns, 64 microns across, and they're hollow. They have a little bubble in them, and so they actually float. And they want to spread these all over the Arctic. It's just nuts. In one of the videos where this woman, Leslie Fields, is the principal investigator on it, I put on one of the videos because glass is something I know something about, and I said, you know that there are 2 tons of CO2 emitted for every ton of glass, and she didn't know that. She said, "Oh, that's something to do with the glass industry." But I went to make sure. I've written stuff up which was, at least 2 tons of CO2 to a ton of glass, with, natural gas is the commonest thing to melt glass. But all the things that I could find said 3 tons, 3.04 tons for every ton of glass. So every ton of those microspherules you spread on the Arctic, you're putting 3 tons of CO2. And just the number, there wouldn't be enough silica to actually do it. It's mad. But anyway, Going South then pointed out to me that it's so harebrained because she's got it wrong. She thinks that it's like, they did a test in a lake in Montana. They sprinkled the stuff on the lake, and then of course it was insulating. But what Going South was saying was, it's not the solar radiation falling on the ice that's melting it. It's the ocean currents underneath it. So it's got nothing to do with the albedo or changing the albedo. Because the warming's coming from, the influx of Atlantic and Pacific. So it's, and they did tests. I mean, it would be a disaster from the point of view of marine life and uptake on that. But they said, oh, well, it's all safe because they got a tank and they chucked a handful of this stuff in, and whatever the sturgeon, whatever in the fish tank didn't get it. It's like, like windblown glass will, it gives you silicosis. So it would give, seals and whales and things, any air-breathing mammal will get silicosis from this stuff when blown around. And it'll last thousands of years. It'll take a long time for that to degrade. They say, oh, it'll weather, in the seawater. But they don't know what's really going to happen to it. Anyway, it's crazy. It's more the crazy ass shit that these people are trying. But that's we were going to try send a letter, but it looks like it's not going to happen now because other people saw sense. So far, people are seeing sense.
But would it have worked better in the equator, around the equator, then, if it was really trying to affect the albedo, reflect more sunlight?
Yeah, really to hold. I mean, you could just put white paint down. If you just want to use the brightening effect, you could, put it in the tropics with white paint. I mean, they have super white paint now, and they could start painting cities. But you see that what's silly about these things is the sheer scale. So you have to have a look at the manufacturing footprint, and everything has a huge carbon footprint. Any manufacturing process just about has a huge carbon footprint. And then, it's so you have to offset that. And then these things are environmental hazards. You can't just start sprinkling stuff around. And you need tons and tons. I mean, we're talking 6,000 times. We worked out on the back of an envelope. You'd need 6,000 times the output of the current glass industry to you know, to do like 1% of the Arctic ice. It's like crazy. Crazy. So it's never going to happen. There's no way of dispersing these things. And, you know, by the time you've actually got some dispersal mechanism, you've got to factor in all the transport costs and stuff. It's all a losing proposition. But yeah. So, we lost Ryan there for a second. Yeah. Anyway, so that was that. Does anybody want to talk any more about it? Yeah, Sintef in Norway. They won't deploy before it's cleared by scientists in Sintef in Norway. So Sintef is the Science and Technology Institute, I think, in Norway, and so they'll get some sanity check on these people. Then it's the effect of waves. If you've seen pollen in the lake, yeah, it tends to back together into narrow bands. Yeah, well, that's what I thought. I thought you know, they spread it really thin on a lake in Montana, and they did it with a spreader, you know, basically a seed spreader, and so you can't do that in the Arctic. And so it'll be, you know, if you've seen a snowblower or something like that, if they spread it like that, they're thinking, well, you can do it about, you know, 6, maybe half a millimeter, less than half a millimeter. There's no way you'll be able to do that because you know, it'll go like sand dunes. It'll start getting ripples and stuff in it. So you can't do this. It's mad. You would need a lot of it, thick, and then it would be windblown. You'd have this windblown abrasive glass. It's nuts. It's just, you know, you have to pinch yourself and you say, we're doing all of this, we're proposing all of this because people don't want to stop. You know, we've had the revolution now since 1750, but we've only had electricity for 100 years, and we've had, you know, the grid and, you know, really the great acceleration is the last 50 years. So in the bullshit we've done in my lifetime, they're doing all this desperate stuff because they don't want to stop. They don't want to roll back to, you know, the year I was born in. That's how addicted we are. They would prefer to risk the entire planet than just roll back the economy 50 years. It's like, wow, we are pathologically sick.
Yeah,
We have to stop.
One thing I've been, you know, just kind of frightened of for the past 2 weeks, because I didn't realize it was an issue, is the poisoning of the oceans with all the toxins from cities around sea level, from sea level rise. Like the amount of absolute horrible toxins that are in our cities that are going to be under the ocean is going to leach out into the ocean. And I thought about all of the you know, what kind of effect that's going to have on the ecosystem there, and then to move all of our cities away from the coasts. The amount of fossil fuels needed to do that would completely defeat the purpose of trying. And you know, to just clean that up, purely just clean that up would be, you know, an enormous. It'd probably take the amount of a yearly GDP of Earth to do just back of the napkin calculation or whatever. I haven't done any of the math for it, but it just seems like an insurmountable amount of effort that people couldn't afford to do, and it would require enormous amounts of fossil fuels, so it would backfire even if we tried.
Yeah, you know, in the US, and I think around the world, really, most most harbors, ports, especially if they were used by the Navy, are Superfund sites. So all the ports in the US, they haven't cleaned them up because it's too expensive. So and they're all within about a meter of sea level. So when the sea level rises, basically then the cleanup happens with the ocean. But all of this, all the toxins from cities are coming into the ocean right now from runoff. And it's something I know very well because I make my water from a desalinator. And I've got to, like where I am now is like a small little place. It's not very big, but I can't make water here because the water's not clean enough. I'll contaminate my tanks. And so it's not that they pumping sewage and stuff into the water. It's just that you have rats and wheels disease, and dead cats, and the cities are extremely dirty, toxic, full of entropy, and disease, and so and all these chemicals. So these are flooding continuously. This city is just a weeping sore into the sea. It's either into a river first or into the sea. So I can't make any water, except miles away from a river mouth or from the shore, from a town. So I see it. People don't realize they think the sea is just a dumping ground, which is an infinite dumping ground. And it's what's probably going to happen is that with the temperature rise, life on land will become untenable and it will return to the sea. And everybody thinks of it the other way around. They think the sea's going to go. If the sea goes, life on land's an afterthought. So yeah, but yeah, there was something else that I want to say about the. Just to rebuild all those cities. It's an interesting thing. I met a guy a couple of years ago who was sailing, a Dutch guy, and he was really into this project. He is a rich guy, and he was into all these environmental things. And his big thing, which he shared all the documents with me with, and that was for this carbon-free concrete. So you can make concrete. They went back and looked at the Roman recipe and the Chinese recipe and the Great Wall, and they said, concrete is so energy intensive and puts out so much CO2 because of the lime. So he said they developed this, or the research. This is the problem with scientists and these geeks. Is they think that these are engineering problems with engineering fixes, and it's not an engineering problem. They engineered concrete that had zero CO2 emissions, and you think, great, concrete is like something like 10% of the CO2 emissions around the world, and you think, okay, that's eliminated 10%. No, they couldn't get anywhere with this concrete, although they've solved the technical problems, and then it can scale and everything. So no one will touch it, and the reason is because concrete around the world is run by the mafia. So they went to the mafia guys and all the unions and stuff that you have to jump through hoops if you want to pour concrete, and they said no, we can't touch it, because they said it's a very they have all these arrangements. They're all crooks, right? They all have all these arrangements so that the guys who gets the lime is part of a monopoly, and if you cut him out, you will get a gang war around the world with these concrete guys. They're not going to touch the relationships they have because they're very delicate. They're very old relationships, and these are guys that'll break your knees. So the guy's saying yeah, we love your concrete, but no, we're not going to upset all the the status quo of the concrete industry for you. And so he's going to governments and stuff like that. And the governments are all owned by these guys. The government's all in their pocket. Now, scientists don't do that. You see endless thing on the article, all these guys like Dr. Leslie Fields there. She's saying, this is a technical problem. We need technical fixes. No, it's got really almost nothing to do with technical problems. And so so what they're doing with engineering, what David Keith and all of these guys are doing is, these are all the naive, out of touch ivory tower geeks that have said, like, we've tried for 30 years to try and get to change the political system and the social thing. They said it's just too difficult. We can't engineer people. They're just too difficult. So what we're going to do is engineer the planet. If people are too difficult, let's see how we do with the ecosystem. So it's that same engineering mindset saying it failed to do social engineering. Now we'll just try climate engineering. And so, and all these kids have faith in that. They all say, yeah, science, insulate Britain is, we will take over the government, and then, we'll set up citizens' assemblies. They'll all be advised by scientists. It's like, wow, so naive. Yeah, and so anyway, Ryan, unless anybody's got anything else to say, the last time I thought, last weekend, I thought that you were going to be on the Eastern one, Eastern Extinctionati meeting, right? So we talked about AI on that one, thinking, oh, well, you're not going to turn up. And then you turned up on the Western one, and we talked about something else. But I would like to, unless anybody's got something else they want to talk about, I would like to go into artificial intelligence again, and particularly, I'm very keen on pursuing what exactly is intelligence, because it's a good route to wisdom and to self-knowledge. And so I think as I said, the genesis of AI is not to solve all our problems. It's to show us who we are. It's a mirror, because it's not intelligence; it's anti-intelligence. And so it's by studying it and asking exactly what is wisdom, what is intelligence, then you can start to see what human intelligence is. And I think that's the start of getting an epiphany. Does
Sounds
anybody
good to
have
me.
anything? Okay. Yeah, so I don't know if you watched the last one, but okay, there's something which I'd like to highlight, and it's really quite intertwined with stuff like geoengineering. So geoengineering, if you see the one that we did this morning talking about David Keith and solar radiation and the measurement problem and cybernetics, it's really, if you try and control a complex system, like David Keith thinks you can, because he doesn't understand feedback. He thinks that it assists you. He doesn't realize it screws you up. But anyway, all of these cybernetic systems were the genesis of cybernetics and some of this machine learning and stuff like that. So, and then you had Paul Shannon's mouse, Theseus, that could do mazes, mechanical mouse that could do mazes, and would get stuck in a feedback loop and start going round and round in circles. And the guys like Margaret Mead and Jeffrey Bateson and stuff were very excited about that, because they said, you've recreated a human neurosis. And I think you did. That was a mechanical version of a human neurosis. But okay, but so here's what I want to propose to you about tackling what exactly intelligence is. And I think that again, everybody, what I said before about AI is upside down. The AI engineers and stuff are thinking upside down, and I think Turing and that was thinking upside down too. So just for everybody else who isn't into software engineering and stuff, if you open up a textbook, very first page of a information science textbook will say, what is a computer? Well, some version of this, and it'll say it's an input, and then a process, and then an output. And then why these guys have it upside down is they're saying, by looking at the output, we can tell if something's intelligent. And I'm saying, no, you can't. You fundamentally, mathematically, provably cannot. So there's that one video that I posted where the guy was saying, about an IQ test, the math logger. video, where he was saying, you know, any sequence, you can have any sequence you like, and you can show that it has a valid algorithm behind it. And so the IQ tests are nuts. I told you about it at our school, where I said that, you know, we came to the conclusion that an IQ test is just seeing if you can figure out the thinking process of the guy that set the test. There is no logical answer to any of the, you know, spot the odd one out or what's the next in the sequence kind of questions. And it's mathematically provable that way. So you're saying, well, then what is the, you know, what is an intelligent output? You say you couldn't say. You won't be able to say what an intelligent output is. So let's think about something like, you know, something can sound intelligent, but it might not be. I mentioned about Seoul in the Chinese room, and they said, you know, it can mimic somebody can, you know, just by following rote learning process, they can imitate as if they can speak Chinese, but they can't. They just know when you get these characters, go to this store and give this response. And so
I can give
they don't really understand Chinese.
To that's similar to that the Searle example, the example of speciousness. So a wasp of a certain kind, I forget what it is, but the wasp's scientific name is Sphex something, and the behavior is these wasps burrow into a particular hole, or they take over a burrow, and they lay their eggs in there. And this particular wasp goes out and finds like a grasshopper and stuns it and brings it back in front of the hole for the larvae to devour. And this looks like very intelligent behavior, like it's forward planning, it's anticipating the needs of the larvae, and you'd think there's just so much cognition behind it. But if you move the larvae over by 1 inch, the wasp just goes oh and flies out and gets another one and puts it right next to it, and it clearly doesn't notice that it could just bump it once, like a few centimeters over, and it doesn't know that that's actually there. Another example is like the albatross can't detect its own kids if it falls out of the nest, so the kid just dies, right? If the because it can only detect that it has stayed in the nest. So it's very, very primitive implementation of an algorithm that's hard-coded to give seemingly intelligent behavior, but is clearly not intelligent, because we're just assuming intelligence behind that hard coding when there is none. It's just part of the genetic code or part of the patterns that are often established. So it's similar to Searle's Chinese room, like looking it up in a database, because it's essentially a hard-coded lookup in the wasp's mind. It's a simple pattern that it will do regardless of whether it knows what it's doing.
Yeah, I think it's called a fixed action potential.
Correct.
It's just an instinct. It's not actually doing computation. So yeah, there was another brilliant example from the animal kingdom that I just thought of while you're talking, but I forgot by the time you finished. What was it? Was also to do with insects, I think. Or maybe birds. Yeah, but anyway, it's there are lots of those examples in the animal kingdom which show that these are not making intelligent decisions. They're just responding to a very basic action-reaction pattern. And so Okay, so now what I wanted to do was to propose something to give you an example. Is to say, okay, let's take it from the point of view of an unintelligent response. So if you have, say, a Turing test of some machine or some process or entity, say, is this machine intelligent? You'd say, well, if it gave random responses, you would assume if they didn't have any pattern or structure, you'd have to say, nah, this is a stupid thing. It's only when it seems to understand you and responds to the patterns that you have in your head that you start to say that it's intelligent. So, so looking at it from the point of view of an output, then you could, if you go with me on this, then you'll say, well, like, if I give you a random output, then you'll be able to say, well, this is not intelligent. And at least you can strike off some subset of unintelligent responses. Now, most people would think, okay, we're all on solid ground. This also, by the way, just as a tangent for what I was talking about this morning with David Keith and the measurement problem for actually doing, sulfates in the atmosphere, is it's terribly difficult to monitor what you're doing in terms of, because it's cybernetic and it has feedback. So it's much like the autopilot on a yacht or a boat, and it has gain and response, so those two parameters. And so, David Keith was talking about pilot-induced turbulence, the example that I used, funny enough, to explain to why you don't want to do this. But he and his team, they still don't seem to grasp the fact that you can't do measurements. They were talking about doing measurements, saying discretely, saying that, you would do intermittent amounts of these injections of sulfates in the stratosphere. And then that would show you that, you could see little peaks and stuff. But saying it doesn't work that way. You can't actually do that. So you would still have noise and clusters and stuff. It's not that simple. So you could put a pattern, say Morse code or something that couldn't come by accident or something, and then you'd know that your readout of, say, whatever, the global dimming or the temperature, where it came from, was correlated to your actions and not just to chance and things like that. Okay, so now here's the interesting thing. So if you go with this idea that say a random pattern is unintelligent, or you'd say then that you can tell whether something is unintelligent, say a Chinese box, then, or a bit of AI, then you'd say, okay, that's fine. If it's doing stuff that's not completely random, then you'd say it's on the path to. And all of this might sound reasonable to you, but if it does, you should go and join David Keith, because it's not actually sane at all. It's not valid at all. So here, I'll tell you this little story. I once worked with this guy who was a mathematician and very good at programming, and we talk maths and stuff. And he said he had a very interesting experience where he was hired on contract by this startup company that had just developed this random number generator. So and his task was, as a consultant, to come and write, guarantee to shareholders and investors and stuff that this product was actually putting out random numbers. And he started off thinking, okay, well, this is fine. This will be a piece of cake. I just have to look at, distributions, make sure that everything, things are evenly normalized and stuff like that. And I thought it'd be quite easy. So he started the job and he thought, well, I better just go and look at the science of, random numbers and just see how you do test for random numbers. And he was shocked, because there is no test for a random number. Nobody knows what a random number is. Now, brace yourself a little bit there, because people don't generally realize this, that we don't know what a random number is. So here's the problem. If you have an infinite sequence of random numbers, you should have an infinite infinite array, which is just say zeros, just a sequence of 0, 0, 0, 0. Now, most people would say, okay, look at this sequence of numbers. And it would be some digits that look like they're nicely distributed. And there'd be like 2, 3, 8, 5, 9, 6. And you know, it looks like, oh, you know, it looks pretty random. Well, somebody can easily show you, well, no, that's very compressible. The first sequence is actually from pi. And what you can compress it, say, you know, just burn 100 digits of pi and give me the next 100 digits. Well, that's very compressible. And it's not random at all. It's digits of pi. So, and then you look at all the zeros and you'd say, okay, well, that is definitely not random. Programmer would just be like print 0 100 times. Now, Gregory Chaitin, who's a mathematician at IBM and very keen on random numbers, and said that you know that it's strange that you can have an infinite sequence inside an infinite set. But anyway, you can. It kind of blows Cantor's mind. But if you didn't have an infinite sequence of zeros in an infinite random number, then it's kind of a proof that it isn't random. You should be suspicious that it's not random if it doesn't have endless sequence of repetition. Now, that's not what most people think, right? So then you say, well, if that's true, then what exactly is a random number? Well, it's bizarre. People struggle with random numbers because, for example, a little while ago, there was a very popular CD that was filled with, you know, random numbers. And it was used very extensively in physics, and scientists used it. There's a lot of uses for random numbers and, you know, control sets and stuff like that, null hypotheses and stuff. So it's very well used. But and the guy said on the CD it's guaranteed random numbers. But here's why it's so daft, because so many people used that CD with random numbers on it. It wasn't random at all. It was, you know, if aliens had come and look at our science, they'd say, oh, I understand what these guys are doing. They've got a CD with the same number on it. It's not random at all. Does that make sense? The mere fact that you stamp out a CD with a sequence of numbers on it and sell it by the millions corrupts the idea that it's random. It's already been duplicated a million times and put out there as a fixed number. So so they were lying on the CD. The mere fact that they released it commercially in large numbers meant that it wasn't random. So then faced with all those, you say, well, what is a random number? And so Gregory Chaitin said, you know, that you can only know by knowing the source. You cannot know from a number whether it was random or not. So he says that you have to look at the process that generated it, and only by examining that process can you actually say whether it's random. You cannot tell from the output, which is not what a lot of people think. So it turns out that there are only very few random sources in the universe. There's pseudo-random numbers which are not random, but and in your computer, random numbers are pseudo-random numbers. They have a pseudo-random number generator. But by the way, all of this stuff is very important for cryptography and stuff on the internet. So, I mean, it's not an obscure, abstract thing that's unimportant. The whole of the internet and commerce and then military cryptography and stuff is based on these kind of like random number seeds and things like that. So anyway, it's a very important topic. But it turns out that there are only a very few sources of truly random data that they can find no structure in. And one of them is atmospheric noise and one of them is quantum noise. But that's pretty much your lot. And even then there's a little bit of signal in the atmospheric noise. But Ryan, do you want to say anything on random numbers?
On the cryptography part, because it's so hard on a computer to create something that's cryptographically random, where you can't predict the outcome by knowing, guessing the seed. Like your operating system actually collects a pool of entropy from your behavior all the time. So moving your mouse and typing random keys and these kinds of things collects some randomness from outside of the computer's normal operations from the real world. And it uses that whenever you, say, generate a key pair where you're trying to do some cryptography and keep things to be more secure. But you can run out of that. And there are attacks that deplete your entropy, your source of entropy, by generating a bunch of key pairs a lot of the time. And then it becomes predictable after a certain point, where you can know which kind of random number your computer's going to spit out. So there's all kinds of attacks at that level. The other thing I was going to say, that was just a kind of an interesting tidbit, but in terms of the, I think randomness itself, it's good to say it depends on the source, but I think ultimately this is one of those concepts that is malformed in a way because it didn't seem to need a definition, because most people understand it through analogy. So when you're saying, oh, just throw some 6-sided dice around and you'll get a random number out, and that's how it's introduced to us, but it's never introduced in a formal way, because I think there's an innate sense of unexpectedness with a random number, and that expectation lives in our head. It's not in the mathematics. It's not in the world itself. So when you try to actually define what randomness is, it defies a definition, right? Because it's inherently subjective to the observer. And this is, I mean, you can define certain, statistical properties on a distribution, but that doesn't determine whether something came out, whether that was, as you said, there's a source of randomness, which is just a sequence that's evenly distributed, but that even distribution is also an expectation, because you could have the sequence of 1 to 1,000 be a random number. It's just, it would defy our expectation to see that. So we see patterns all over. That's what our brains do. And if we see a random number source that comes with a pattern, we think it's not random because of that. But often those patterns are more likely, are likely to exist. And so our intuitions need to be thrown out when we're dealing with probabilities, with randoms, with exponentials, all those little dangerous things in mathematics where our primate brains fail. And I think this is another case of, entropy is something you've brought up before, Hugh, where this is something that has always been bugging me about how entropy is introduced when it's explained in physics. Usually, of you can't unfry an egg, or you can't put back together, you'd see a coffee mug falling and shattering into a bunch of pieces, and saying, oh, this is increasing the chaos and the entropy in the system. And the thing that is missed by most of the audience, if they see a clip like that, is that the reason that has an effect on your brain as you're processing that is because you have object recognition for the coffee cup. And then that expectation is dashed when it shatters. But the universe doesn't. It doesn't care which piece of the coffee cup was where, right? There is some, ionic bond there, and now it's somewhere else. It doesn't, that object permanence is a heuristic that our brain puts into use to simplify and compress the world. but it does not. It is not the world. And when it's explained mathematically, maybe there's some sense to entropy. But when it's explained by analogy, it's exploiting a weakness of our cognition to make a false understanding of what concept was just introduced.
Yeah. Okay, so that's good. So what I was going to propose now, well, just one thing on what you said that I would slightly disagree with is that you can tell if something, while you might not be able to tell when something, a process is not random. I mean, is random. Wait, you might not be able to tell whether a process generates a random number. You can tell that some processes will not generate random numbers. So in other words, if you have a program that just says in a loop, just print 0 100 times, execute 100 times, then that program, you could examine the mechanism and say, okay, I know that this sequence of 100 zeros came from this program, and so you can see logically that is all it can do, and therefore it's not random. So you can actually say in Chaitin style
that there is no general purpose algorithm for determining whether a number is random. Just like there's no general purpose algorithm for determining, like for solving the halting problem. But in specific cases, you can tell that the program holds. Like it's just that kind of analogy.
Yeah. Yeah. So what I'm going to propose now is that, like the Chaitin randomness is, I would propose that also intelligence is the same. It's, as Ryan said, it's not a well-formed idea. Intelligence is not a very well-formed idea. We have a rough idea, like we do with randomness, and it's not really quite valid from the universe's point of view. Now, I would go against what all these people are saying. Every time they're, you have GPT-3 and stuff, and there's AI comes out with something, they say, look at its output. It's intelligent. I'm saying, no, that doesn't make, its output doesn't make it intelligent. You've got to look at the process that generated the output to decide whether it's mechanistic. And if it's repetitive or bounded, then it's not intelligent. So in other words, it's clockwork, and clockwork is not intelligent. So then you have to say, well, if it is intelligent, then it wouldn't be a clockwork mechanism. In other words, synchronous. It wouldn't be chronological, right?
I'm sorry to interrupt you there, but I've heard you use this term clockwork a lot, and the thing that's missing in clocks is the feedback mechanism, which can send things into new territories that are not, say, algebraic numbers or something like that, where you have the ability to get chaos and inject it into the system. So clocks, if you just have something clockwork, it does not span the set of all things that computers can do. Because
yeah, but I'm just meaning the special case of the inputs to a clock are winding it up or giving it energy, and then the outputs are like the dials on a hand or something like Boole and Babbage's difference engine, something like that. It's something where you just crank the handle, you set the knobs, crank the handle, and then get an output on a ticker tape. The classic idea of what a computer is. So then I think, yeah, this is what the cyberneticists and that got excited about, was the fact that if you start implementing feedback, if you start feeding its tail on it, then suddenly you get all sorts of complex behavior, and then so somewhere down that path must be the path to intelligence. So before you can say AI is intelligent, you have to look at the mechanism and say, what kind of feedback process does it have, and then what kind of patterns does it generate and why. So
yeah.
Am I still on sound ground then, Ryan?
Yeah, I think this is a relevant distinction, because there are many schools of AI, And many of them are in the clockwork school. So if you're doing expert systems, if you're doing, in some sense, even the Bayesian inference stuff is somewhat fuzzy clockwork. Fuzzy logic, there's all kinds of theorem proving type of AI where you're trying to program the rules that you should behave. Like a lot of the self-driving car thing, like you put in some rules about how the road should behave, how you should work with things, and those tend to be very brittle in novel circumstances. So if you and this is where I think what caused the AI winter in the 80s is that there was a big attempts around this kind of clockwork AI, and people realized the limitations of this. So Japan built this 5th generation computer that was essentially you were going to program the world's knowledge into it, and then have it, theorem prove your way out. The problem is that these different little rules, once you get beyond like 300 of these rules, it causes such an exponential blow up in the search space that you never get anywhere. So it was a fool's errand from the get-go. But once they spent these huge sums of money trying to pursue this clockwork idea, and got almost nowhere. I mean, they got a few successes like jet fighter AIs that could like soar, that they were able to implement through these logical rules. But it's essentially child's play. It's what you would program. It always fails on certain inputs that you give it. Now, this is what's interesting about that is even the deep learning models that have come out, even though they incorporate a lot of fancy mathematics, very little actual randomness in them, except for the topology of the network or what have you. But they usually use calculus and continuous mathematics to try to implement the deep learning. So it is somewhat clockworky, but for any of the detection algorithms, say you have a cat detection algorithm and something that can tell between cats and dogs or something, you can there's a paper that proves that for any input that looks, you can add a bit of noise to it to trick the algorithm into detecting something completely else. This is completely different. So you could print out, say, a picture of a cat that looks exactly like a cat, and the AI, if you know what the AI is doing, you can create an adversarial example of a picture of a cat that will say it's like 95% a dog, right? You can't, and this is actually one of the really dangerous things about letting these algorithms out in the wild, because if someone has adversarial examples, that they can print out on a T-shirt that will cause your self-driving car to interpret that as a shopping cart that's moving or something like that, you could kill people by just having a picture out in the world. And there are other ways that this could be exploited as well. But I think that kind of separates that there are usually two camps. One which is like strictly I'm programming the logical rules in, and that's very clockwork. And then there's more of the smooth, continuous, random number, pseudo-random number generated basis of AI, and those are different algorithmic categories.
Yeah, but what I'm proposing is that the more deterministic ones are not, you wouldn't class them as intelligent. I wouldn't say that they are on the path to intelligence. So in other words, anything that has a perceptron and a neural net and an output, kind of like the image recognition stuff. They're not intelligent because they just really reflect the training set that you gave them, and that's what Google found to their terror when when they found that they couldn't discriminate. The image recognition couldn't discriminate between a black couple and gorillas, just because the training set looked like gorillas. So it hadn't been given enough examples of black people in the people faces. So what Google did was they just took any reference to gorillas out, because I bet I know what they did was they found that when they started putting black and white faces together, then the algorithm degraded terribly for recognizing faces, because they're quite different, and so you're covering too much of a data space that's too disparate. But all of those kind of perceptron or image recognition kind of things are not intelligent because of the example like of a toddler could figure out from, if you had lots of examples in your training set of animals, most of these are trained on a very specific set, just like the CD of random numbers. There's an image set that they all use. It's a free image set. But for example, if you had lots of animals and you had just one picture of a lobster, it wouldn't be able to recognize a lobster unless it was a perfect fit for that lobster. In other words, it's not getting a generalized thing about what an animal is. Even a toddler would know that a lobster is a creature, and just given one lobster, just a picture of one lobster, you could release a toddler on a beach, and a toddler could run up and down the beach and find one for you. But you won't get that with image recognition. So it's doing something fundamentally different in a human brain. So, yeah, did you want to say something, right?
Yeah. I was saying, I think that particular issue about it not being able to abstract to general categories, I don't think is a fundamental limitation of the technology. I think that has been demonstrated that can work. It's in the early stages of the technology that was a limitation, but there's active research in that area, and I don't think that's something fundamental. The other thing that I want to ask is, a perceptron is a particularly hobbled, primitive neural network, and I wonder if you would take a particularly hobbled actual neuron or a set of a few neurons and say, is that also equivalently unintelligent?
So that's kind of where I'm going with all of this, is saying that if you have a look at the processes and shape and style, what they are liable to produce, then you can say, well, okay, we have an example of what we originally called intelligence before we started on artificial intelligence, and it's us and our brains, and it's the human brain is really what we're after. That's what Turing was after. And so you can have a look and say, okay, so since you have one example of a mechanism that does generate intelligence, how does its operational parameters differ from the artificial ones? And the first thing you can see is that what neurons are doing is fundamentally very different. Although they fire, so you get spikes of electricity on them, they're working quite different to what most AI is implemented in software, but it's certainly very different to the hardware of the computer. So, for example, they have some of the things that it's doing is self-organized criticality. There's quite a lot of evidence that they have cascades of things. So if you just trigger one neuron, it doesn't just fire and just in an isolated way. It cascades and gives a shower of neurons. There's quite a bit of research that says that it's fractal, because you can show that it's scale free, and the various cascades have normal distribution. So it's saying that it's doing something fundamentally fractal, which is not common in AI. So if you and it's very subject to feedback. There's in Hofstadter, who is kind of an early AI apostate. He worked on AI in the 80s and became a complete non-believer in AI. And he wrote a book called I'm a Strange Loop, which is saying that humans fundamentally are a strange loop. It's has feedback pretty much like putting a camera on a monitor, on the same monitor, on its own monitor, and then you get these complex forms that are fractal. And so our brain seems to be doing exactly that kind of thing. And I haven't heard of anybody being able to model anything like that in AI. But I just want to show you just how an example of just how different, let's say, the hardware is why I say that AI is kind of the opposite of intelligence. Is it's coming from the opposite angle. As we get closer to Moore's law, well, a kind of Moore's law has been reached now. They just replicate cause laterally now. They just have parallel processing because the end of Moore's law, but maybe even by 2008. And so the reason we couldn't go any smaller in terms of nanotechnology and silicon wafers is because of the heat, and they're starting to get to the quantum level and starting to get quantum interference. Now, I think a human brain is doing the opposite. It's using randomness, quantum interference, and somehow intelligence emerges from that. So the fact that we're starting top down and getting to the quantum level where we kind of get thwarted with AI, our brain's coming from the opposite direction. It's coming from quantum processes that then scale up to some kind of emergence intelligence.
Yeah.
But
so to
yeah,
this
you want to say
point,
something?
yeah, I have something I want to say there. So to this point, I am not convinced yet that the action potentials in neurons are quantum influenced at the scale where the action potential is actually being propagated. Because that quantum stuff with your Roger Penrose and the microtubules and all these things, that's a bit of woo, honestly. It doesn't have enough of an effect to make the macro structures of what's happening at the cellular level be massively guided. However, I will state that there are cases in evolution that have leveraged quantum effects, and that is the van der Waals effect. Of if you put two plates very close together, the quantum weirdness in between them will cause them.
Casimir effect.
Casimir? So
Yeah,
maybe that's a different one.
Van der Waals forces are just weak nickel. It's Casimir effect.
Okay, so I'm thinking of so maybe I'm explaining that effect wrong, but I think the van der Waals effects are being used in the gecko's foot. So
yes. Adhesion is van der Waals forces. Yeah. The Casimir effect is with two plates. Yeah.
Okay. Apologies for conflating the two concepts, but that is the reason a gecko can stick to like a perfectly smooth, atomically smooth surface with their feet is that they're using quantum effects at the adhesion level of their foot pads. So that is something evolutionarily arrived at that does leverage a quantum effect. So it's not impossible for evolution to reach to that territory in the case of neuroscience or whatever, their neurology, but I don't think that that claim requires some extraordinary evidence, I think, to back it up.
I don't think it's as rude as you think. So, so what's happening with the gecko's foot is you essentially have branching. So it gets, you know, these kind of feathered branches on its pads, and they get finer and finer until essentially you're getting to quantum scales, and at the end of those. So I think neurons do exactly the same thing. And so what they've discovering now, I think, is that the model of the neuron is too simple. The idea is just, you know, builds up a little potential and then pops and spikes, and then, you know, you get this propagation going forward. Is they always have, you know, show you in this kind of diagrams that you have this kind of little pad and foot arrangement where the neuron sits, and you have these neurotransmitters that bridge the gap, and they show you that dopamine blocks it, and they always do it as, you know, sprinkled little symbols or sprinkled little molecules on the foot. And I think what they're finding now is that they're complicated structures. So the receptors and the chemicals, they're not just randomly distributed. They have complex shapes and patterns. And all those there's some intelligence in those patterns. So they're not like the little diagrams where they draw, you know, little snow coming out and say, and the neurotransmitters do something. They're, you know, it's like the foot of the gecko. It goes down to infinite scales of really, really tiny structures and complicated structures. So they just getting to have a look at those, and then you start to see all these amazing patterns that you would think of as more like a fractal landscape. And so I think that there's definitely something to do with fractals going on, as you bore down on it.
Oh, I definitely will agree with that.
Is there anything you want to say?
Yeah, I want to respond to that. So the typical artificial neural network model neurons have nothing to do with actual neurons. Like they're essentially glorified circuits, right? But actual neurons are much deeper biologically. Like, for example, the neurotransmitters that were mentioned, all the different neurotransmitters involved in a neuron's functioning and regulation are ignored in artificial neural networks. They're just not even considered. And that's, with some exceptions where people are trying to like kind of shoehorn them in because there is a biological analog, but it's largely ignored. And I think if you are to look at the structure and how neurotransmitters affect different parts of the brain in drastically different ways, and regulate things like that. I had an idea earlier for how you could create targeted, like drug targeting, is if you had a vesicle with a drug in it, and you had the ability to kind of count the neurotransmitter receptors of a particular pattern, you could kind of localize to a certain region of the brain. Say, this, use that as an addressing mechanism to say, oh, you are near the pituitary gland now because this the neurotransmitter receptors are of this in this proportion around you, right? It wouldn't work because blood-brain barrier and a bunch of other reasons, but it was an interesting thought experiment when I was doing some of the neuroscience stuff. But I think we have to look, if we're trying to really wrap our heads around how neurons work, you have essentially there is a message passing mechanism in a way. Like there's that calcium wave that passes from neuron to neuron. That is that's kind of a discrete thing in a way, except that the structures of the pathways that it takes are fractal. So the dendrites actually go and reach to multiple places, and the shape of them affects how quickly they diffuse that calcium wave and how quickly and how many other things it touches. So the actual topology and the shape of the neurons has a lot to do with the computation that it performs. So the message reaching you at some point, that's a discrete thing. That's computable. That's something we could do on a computer. But the actual shape is really complex, right? You'd have to model it in 3D and like simulate things along it, and it would be enormously inefficient to even get close to an approximation of it. And I think this is where we're getting into the point where you can start to describe some of the fractal effects that you're talking about, because it's in fact these subtle tiny so one of the problems with artificial neural networks is they're often trained based on the weights between the edges of the neurons, like the connections between the nodes. And these weights are just assumed to be, as you train a neural network, you are training the weights on it. However, a much greater effect on the performance of a neural network comes from the topology of the network, how the nodes are connected, how the neurons are connected. And often this is just, slap it on a grid and hope for the best, right? And so when the AI researchers are ignoring the topology or they're creating a layered topology where they're saying, okay, here's a grid of artificial neurons, and then here's another layer of artificial neurons, here's another layer. That's clockworking it, right? Where you take different slices and say, here's a complete layer, and here's a complete layer, and here's a complete layer. In the real world, neurons are completely, in a more of a chaotic mess. There are columns of neurons, but they're not in the same layers like that, except in the V1 and V2 neurons in your the occipital lobe, right?
Myelin sheath, or basically the upper,
very few cases are they actually laid out in that clockwork structure of like lasagna. they're often in a web in this scale free structure, right? And one of the so there's a company out of Oxford that designs video game AI, and it's called Natural Motion. And what's very interesting about this group of people is that they created they had the hypothesis that the topology mattered. So what they did is you can look them up online. They have animations of these virtual life forms, essentially. So you build, the idea is you have a bunch of characters, humanoid characters in games, and they have muscles that drive their motion of their skeletons, right? And those muscles are triggered by neurons in an artificial neural network. And that artificial neural network has a topology that's evolved with a genetic algorithm. So it uses it takes generations where it starts randomly giving you neurons and then says, okay, the fitness function is if you take a single step correctly, then you did better than someone who didn't do a single step. If you take 2 steps, you're better off. And essentially to try to train it to walk from nothing, start from zero and just train it to walk. And originally it just flails on the ground. And then after 20 or 30 generations, this thing is walking naturally like a human. And it's not a baked in animation. It's something where it's actually driving an artificial body, right? And they're using this topology of the network as a major tuning parameter to that evolution is saying, okay, this shape of the network is better at walking. And then during the course of its training, it can actually change the weights and stuff to learn better. But it's the broad strokes, the most important thing is actually the shape. And that's largely lost by most AI research.
Yeah, so okay, you've covered a lot of stuff here and about a million things to say. Okay, so but just let me absolutely agree with all of this, and I think where I'd like to try and get to is an idea that you can't just like switch on the lights and start doing some training algorithm. Even an evolutionary thing like what's the name of motion stuff, without running up against the problem that we've had, 3.4 million years of evolution. So at some point, your AI system is borrowing human intelligence. Certainly for all the kind of image recognition things and a lot of the stuff that is AI is supposed to be AI. It's not really. It's just it's leaning on humans AI and trying to get relationships that like a Chinese box. It has no intelligence itself. It just knows that humans have some innate reason to connect to things. And so it manages to cluster things and mimic intelligence that's really got to do with the programmers and the people that set up the training algorithm and the goals more than it does itself. Whereas biological things have a pattern that's been evolved. So the intelligence has come out of evolution. And so intelligence might be a very long, drawn-out thing. It's not something you can just cheat and do by brute force, by trying to catch up with evolution by doing 10 million iterations of something. But okay, now I just wanted to go back to the Wu stuff on the, Penrose and those guys. I think that there's other evidence that there's quantum effects. And one outside is if you take things like cosmic rays and look at, say, the damage that a cosmic ray will do to a computer, then transistors are generally made on some kind of grid lattice format, some kind of circuitry like that. And generally, when you get a cosmic ray hitting them, it takes out one bit. So there are all these classic things about how the selection was thrown by 4,096 votes and stuff, and they showed that it was a bit flip due to a cosmic ray. But then you only get a 1-bit flip. Now that doesn't happen with a neuron. So if you have a look, so there's a famous case of a guy in Russia who stuck his head in a collider, like a linear accelerator, like the Large Hadron Collider. It was an accident. The warning mechanisms weren't working. He walked into the room where this had a beam that was in the free air, and he put his head right in it. And he lived with a lot of trouble. But it's interesting to what he said. He said, now it came and hit him in the nostril and came out the back of his occipital lobes. And he said it just looked like 1,000 suns. He said just this massively bright light, which is kind of interesting. Because if you think of what that is, it's a very, very tiny beam. And most of it will be stopped by the water in his head. It wouldn't absorb all the energy. That's why he's still alive. So it wouldn't, it's kind of wasn't enough to block all the radiation. But it's very interesting that he said that, it's a very, very bright version of what astronauts see. So the astronauts, when they're in orbit, they started seeing all these flashes of lights, and they eventually figured out all the cosmic rays hitting their brains. Now, I don't think they know whether it's hitting their eyeballs or optic nerves. I think it can hit anywhere in their brain and they can see a bright light. If it causes a cascade in the occipital lobe, it'll cause a bright light. So that means just one charged particle can initiate some self-organized criticality in a cascade. I think that implies that there at least is the potential for single particle interactions that lead to large effects inside the brain.
So that seems like
So
a falsifiable hypothesis where we could measure the amount of cosmic rays in a given volume and then measure the amount of perceived white flashes or flashes in a person under those same conditions, and see what percentage of the brain hit causes those. And you could test your hypothesis there.
Yeah, it's very testable as if you just got somebody who just sits still in an fMRI machine for a long while. But ostensibly, you could actually track like any kind of target in an accelerator, in a particle accelerator. You could actually track the splintering through somebody's head and find the exact path that it went through, and then see what occurred on an fMRI. But yeah, I mean, I think you could spray with there's so many. They just switch off the lights and you will see them. There's so many. It would be actually practical to test it. But I think if you compare that, you get a 1-bit flip and then you get a massive effect in the brain. It shows that there are very, very fundamental triggers in the neurons. Well, it suggests that to me anyway. But so another thing that's going on that's not going on in AI and in most neural networks and simulations, which I think makes them kind of clockworky, is that the plasticity of the brain is very, very high. And in fact, it's so extraordinarily high that some bits of the brain are repurposed within an hour. So I saw one neurologist came up with a theory that perhaps the reason why we dream is we keep on refreshing that part of the brain so that it doesn't get co-opted and get used for something else. So in other words, he's thinking of it kind of like DRAM, direct random access memory in a computer. But what happens in a DRAM thing is memory degrades and volatile memory in a computer degrades. So what DRAM has is it has a little circuit that goes and reads a bit and then reinforces it. So it says if it's off, it reinforces that it's off, and if it's on, it refreshes it. And it just goes round and round the memory, continually doing this dynamic refreshment of whatever state it's already in. And
that's an interesting model, but I think it's also there's more to it than that. In that during sleep, there's a difference between your short-term memory and your long-term memory, and there's a process where you take your say your short-term memories and you move them to areas of your brain which are specialized for those kinds of things, so that it's a faster processing later when it needs it. So that's called long-term potentiation. So as you're having short-term memories and you're experiencing those are relatively temporary. But if you had a visual memory, say, it would move more towards the occipital lobe, so that it would be quicker to access. It's like a cache, right? And that's
so no this
that happens when you dream.
So this plasticity. But they're speculating on that. That's just one theory for dreaming. But with this plasticity that I'm talking about is for things like if you remove a limb. So it's or say if somebody's blind or deaf, the circuits that get used for hearing get repurposed and get used for sight and for other things. And so I'm talking about like if somebody has a limb removed, that we have a representation of the stratic part over here, I think, of our whole body. And so if you have a body alteration, within an hour, something else will take it over. It is that quick. So when they discovered just how plastic it was, it implies that, it implies a lot to me. One of the things is how is it organized? If it's so chaotic and there's so much competition for real estate, how does it remain stable? And I think the answer is that it must be self-organized. So it must have an org that must go very deep, and it must have something to do with evolution. It must have something to do with the structure. It must have something to do with the chemistry. But since we only have a small number of genes to express 70 billion neurons, it must organize itself in some internal principle, not only discovery in the environment. So there's something drastically missing in AI, because it's kind of ignores, like you were saying, the internal architecture, and just assumes, inputs, processes, and outputs, that kind of thing, or exploring the environment. And saying, no, it's something as fundamental as tree branching or something like that. Because they know that the Hebbian model is correct, that Hebbian learning is, if it fires together, it wires together. So that is a simple rule that sounds very much like a fractal algorithm. If things fire together and wire together, then they will start to, fight Boltzmann entropy. So what do you think, Brian? Right?
Well, I think, yeah, Hebbian learning is definitely a thing. But you also have to take into account the different modalities due to the different presences of neurotransmitters and stuff. Because that Hebbian learning doesn't factor that in at all. But it's and I think we have that bias in our artificial intelligence models as well, because we understand electricity and wiring things together, and we're applying that. And I think this is one of the problems when we're dealing with these analogies and our mental models when we're talking about AI and or how we see things, because we tend to use our technology of the day as the analogy for our minds. So back in the earlier days of psychology, when we were dealing with steam technology, you would say, "Oh, he's blowing off steam," or we use this clockwork or this, steam analogies of how our intelligences worked, and that is still present in our language in many places, and it's how we think about things. Now we've switched to, we've got these integrated circuits, and so we have our RAM over here, and we have our CPU over here, we have our disk over there, and then we're saying, okay, this part of the brain is kind of like that, and we have these separated modules that are isolated from each other that do things functionally, and that is provably wrong, right? In how our brain actually works. So there is no isolated functionality because of this plasticity, because we have the ability to usurp various modules with other ones. It means that this alien cortex way of like drawing a boundary around stuff and labeling it with a name, that is not actually the implementation of intelligence in the brain. So this is another reason why there's like this whole school of AI that's based on deriving, like encoding ontologies, where you're saying, okay, here's this module, here's that module, they're going to talk, they're going to connect, but they're large organs in the system. That's typical of how you do software engineering, but not how you should be approaching AI, because that's fundamentally not how these systems tend to compose. They tend to not have clear boundaries in the brain.
Yeah, agreed. But there's some ambiguity here, because like, my five-layered brain model is exactly that kind of compartmentalization, but it's not. And so there is specialization on those levels because of evolution. They don't operate independently. So I think maybe trying to do modularize AI is a mistake, because they don't. There's a lot of crosstalk and feedback, and there's a hierarchy, and which is probably not represented in these kind of modules. Like, say, for driving things, like this one does telemetry, this one does spatial recognition, and then you try and wire them all together. But it's correct what you say, that the biology or neurology is not made in those compartments, because nature just doesn't see an end to where the brain starts and ends. And so, for example, your stomach has a large part of your brain is in your stomach. The neurons in your stomach, there's many neurons. It's about as big as a cat's brain. So you have the brain the size of your cat that's in the lining of your stomach. Now, not a lot of people know that, but the brain just, it's the neurons themselves have a large supporting cast of glial cells and all these different types of cells and processes and neurotransmitters. And it's not at all plain that nature sees it as, everything on this side of the blood-brain barrier is brain and everything else is body. And it's the system is so intertwined. It's you're sort of making a mistake thinking of it like a car and saying, well, this bit's the carburetor, this bit's the radiator, here's the battery. There are evolutionary kind of specialization tasks. So it is true that there are functional layers. It's just how they interoperate and how they actually, manage to have this kind of self-organization is the mystery. And I think we can't do AI until we figure out exactly what that mystery is.
So
what is the self-organization in principle?
I agree with you that in order for AI to be properly implemented, it should be probably grown rather than programmed, where you are one of the properties of life that's very different than almost all engineered systems is that from the zygote level, it has to be viable all the way up to the macro phenotype, the organism, right? So if you had you can't just take a bunch of modules and shrink them down to the size of a zygote and have it still be, analogous all the way through. There's some epigenetic process where it grows, and the principles behind the learning and things like that can't be even in the genetics themselves because of what you mentioned earlier. There has to be some kind of a self-organized criticality at a certain scale that makes up for the lack of information in the genome to describe that. And I think what I'm very keen on outlining is that while there are clockwork methods for encoding information in a computer, like if you're using a floating point number, it's very, very susceptible to a bit flip being a very large error, right? But if you're using a different topological encoding where you're distributing the bits in a more of a holographic way, where you're not making you're making it a lot more redundant, and those and having that parallel processing and relying on timings and feedback, like all of those are possible with our current understanding of computing, and it would get closer towards actual what I think we could agree on would be more intelligent. It's not commonly done, but it's not a fundamental limitation of the hardware, I think. there are probably fundamental limitations of the hardware, but the technique we use to implement the algorithms is also a major factor that I don't want to conflate. I think there are the criticisms that you have of the algorithms that are being used, or of AI in general. You're saying they're hardware limitations, and I think in many cases they are simply choosing the wrong algorithm to solve what you're describing. So I want to lay the criticism where it should land, and make sure that we're not making a category error.
No, my fundamental objection is that they are approximations. So they're not doing the same thing because they're not going down to the same resolution. So in other words, it's kind of like you know, a tree as opposed to a lollipop tree. So what we're doing with AI is trying to mimic a tree with a kind of a lollipop version. You know, it's a sketch of a simplified sketch of a tree, and so it's as removed as a lollipop tree from a genuine tree. And so yeah, so I guess we should round it off somewhere here. But what I'm saying is it is a fundamental limitation, because if you tried to, I think, to do a good approximation of intelligence, you'd have to, like you say, start off with embryogenesis, start off with an embryo, have that embryo split, and you would, you know, through genesis, like embryogenesis, you would get to a primitive brain and a smarter brain, and it would self-organize into something which then is semi-intelligent enough to explore the world and wire itself up just like a baby does. And I think you'd have to go that route. If you went that route, I think if you just say implemented each neuron or each cell or anything involved in it, you'd have these 70 billion cells. It wouldn't be enough to just say that, you know, we represent all the states or all the mechanism in one of those neurons with, say, like 1K worth of silicon memory. If you did that, you'd be short thousands of magnitudes of what a neuron is actually doing, because there's structure and pattern that goes probably all the way down to the Planck length. And so there's too much information in one neuron, and it
I totally agree with you on that.
Under the rug. Right.
Yeah. By the way, I think that this is more a criticism for the, you know, Alcor and the cryogenics people, or the people who want to upload to Silicon, is that, yeah, you may be able to get a coarse approximation of the structure of your brain that can, you know, give you similar outputs that your brain would for, you know, for a few seconds or minutes, but then it would drift so wildly that you couldn't simulate it further. It wouldn't be you.
Yeah. Yeah, so okay, so let's round it off there. But I'll leave you with one kind of thought, that if you pursued this line of thought, I think that if you tried to do a very thorough job of mimicking the human brain, you would eventually find that the self-organization comes from something which we don't understand. So, for example, it has something to do with, say, the structure of water, or the fines, you'd have to know the fine structure constant of the universe to actually, get the kind of behavior out of the brain that you see. And so you would run up against a fundamental limit where there is intelligence baked into the structure of the universe, and it's just not accessible to us.
May I add something that is more biological, because that's more my realm? But you mentioned embryology, and you mentioned the early development of brain as intelligence functioning on a material basis. But the tissue of the neuroderm, it's one of the three tissues that differentiate at a very early stage in the embryo. The embryo is made of undifferentiated cells until a very advanced in terms of evolution of its development. So around around a few weeks, around 5-6 weeks, there starts to be appearance even before that of 3 tissues, one the neuroderm, the metaderm, the ectoderm, and each are going to specialize into muscle, skin, etc., nervous system, and things like that. And I think that's where we want to look at intelligence and what you say about self-organization. And I think that's the thought that came immediately into my mind, is this moment, this stage where you come from something that is undifferentiated to suddenly a self-organizing being.
Yeah, I think that's
Yeah, so
really,
this is where I'm
really
going with it.
powerful. Do you mind if I
Yeah,
take
that's where I was trying to go.
Yeah, I think that self-organization, I think, is a really critical principle, and we know that it has to be applied in the case of the brain, because the genetic information isn't enough, right? So, but when you take an adult brain and you try to digitize every neuron in it and make a simulation, that's not the principle of getting to intelligence, right? If you have a simple principle like Hebbian learning, like things that wire together, fire together, that is something that you can encode in a computer. And if we don't understand it yet, it doesn't mean it's from some quantum woo source, right? It could be something fairly mundane in chemistry that we don't understand. It could be just a principle
Yes.
that is complicated that we don't understand in how things wire together, right? But those things are necessarily, like, if you were to encode, the genome in a computer, that's doable, right? And that encodes, some of when you put it in the world, and ribosomes get a hold of that, you can get some proteins that cause some effects, right? So it's the fact, the principle behind the AI that I think, rather than the structure of an adult brain, that might hold the key to intelligence, and it doesn't have to look like our brain.
Yeah, so, but here, I'm trying to land this, but anyway, it's kind of bounced back into the air again. So, yeah, so even when you talk about wiring together in a Hebbian model, I think even wiring is a false analogy. Wiring is again one of these oversimplifications of a process. It's not like getting 2 relays or electrical contacts and wiring them together. The rules for actually branching and wiring must have some intelligence in them. So what I'm saying is that it might be in this infinite regress of knowledge that one thing begets the other. So the reason why I say this is because you see, I've had feet in many disciplines, and I'll just tell you this one thing from the glass industry, which really made me start to have grave doubts about, my colleagues in software and things like that, and especially doing AI and machine intelligence. So when I did this glass furnace, I naively thought, like a computer programmer, that we needed, for this application, we needed to have like 256 different shades of colors of glass. The molten glass had to flow. We had to get a 1-ton furnace, and I thought you could model all of this stuff. And so I had all the best microwave experts in the world and glass experts and everything. And I said, we can do. I started down the path of, because I'm software programmer, I think of doing numerical models to try and model all of these things and use Navier-Stokes and stuff to model the flow of molten glass. And I got into the literature, and I found it was like, this is impossible. It's like nobody knows anything. And I went and asked these guys, and they said, yeah, it's a long-standing problem. It's like nobody knows how to model flowing glass. And I said, what are you talking about? It's just Navier-Stokes. But it says, no, it changes radically. You just put a tiny different ingredients in and stuff. Nobody knows what glass is doing while it's molten. And they've done tons and tons of research in crystallography. And you say, come on, what? They say, no, nobody knows. And then I started to discover that we get given this very thin slice of physics where we pretend we know this tremendous amount. But when you start trying to do something like a glass furnace, you find out we don't know fuck all. So the answer to some people who say like, oh, we might be living in the Matrix, it might all be a computer simulation. It isn't. Because you could do an experiment in the corner where, you know, computer programmers wouldn't know. I could go into the Matrix and prove I'm in the Matrix because I'd melt a bit of glass. And then they'd say, like, I could just prove how it ran and how, you know, different temperatures. And then they would have to do a fudge, the guys who programmed the Matrix, because no one knows for how glass flows and how it heats or anything. So I asked these guys, like, what about the colors? He said, well, you know, you had green, it turns, you know, you have to add iron. Copper, it turns light blue. Make it a little bit different temperature, turns kind of orange. You know, beryllium turns blue, you know, cerulean yellow, all this kind of thing. He said, but what are the rules? I need to know this formulaically so we can feel. And said, like, no one knows. It's just experimentation. It goes back. They only know that cobalt makes it blue because that's what the ancient Egyptians did. Everybody knows that it's to do with the structure of the glass and the, you know, how it's long-range structure and a few angstroms and how it's absorbing them. Nobody can model it because nobody has a clue what's going on. And so I said, like, well, how is anything done? I said, it's all done by experiment. They just, you know, numerical methods, I found out from everything from jet planes to glass and process, you know, manufacturing is, they only do numerical methods late in the day after they've done everything by hand. But even you spoke to an aeronautical engineer, and I thought, naively in my youth, I thought that, you know, jet engines were all modeled by computers and stuff, and then, you know, they didn't start manufacturing them until the thing was all modeled and stuff. It says no, all the thing is done is, you know, the aeronautical engineer says, nah, I think we'll get a bit more efficiency if you add a little flange on the end. And then the fabricators say, how big? And he goes, about that big. And then they go and just try everything. It's all trial and error. And then when you're the last 5% of efficiency, then you start modeling it. But they virtually don't know what they're doing in anything in the world. So by the time you start modeling biology and stuff, it's like we can't even fucking figure out how. And they've tried. Nobody has a theory for glass flows. I was appalled.
Yeah, no.
Anyway,
what you were saying about the structure of water
outside and made progress in that area because I just had a few different ideas that I could try out. So I got some regimes to model the glass, which I should have published papers and stuff. But anyway, I just put that out there to show you how quickly we'd be overwhelmed when we get into the intelligence of actually how embryogenesis works. And, you know, if you go from stem cells all the way up to cell specialization, then that process is some kind of fractal, intelligent, self-organizing process that must rely on things which we would soon run into. Say, oh my God, this is a whole field of chemistry nobody knew about. So in other words, we really have a very, very primitive understanding, but people talk as if we understand the universe and can model it and we have powers that we just absolutely do not.
That's absolutely correct. I think the number of differential equations that we can actually solve analytically is, you know, a tiny, tiny fraction, less than 1%. And the Navier-Stokes is one of them. So if we think we understand, we've discovered the fluid simulation algorithm or the equation for it, we have no clue about what the possible solutions of that are. Like we can simulate it out, but we have no analytical solution for it. And so when you're talking about the finite, like the small structure of water and stuff, yeah, there would be no simulation for that. That we could trust. And in the case of,
and then you would lose part of the dynamic behavior. So that you would say that, you know, this is detectable. It would, because you could look at the mechanism and say, whoever did this doesn't understand how water works at different temperatures. And
Right.
so again, back to Chotem and looking at the mechanism, you could say, this is a fudge.
Right. And I think this gets back to, even if you could say discover the self-organizing criticality algorithm, at the core of that algorithm, like Navier-Stokes equation or something, there's no guarantee that you would be able to implement it in a way that would actually yield the results that you want for a particular domain. And the way that you can organize these domains is similar to how we were able to, try to extract entropy from your mouse movements and these kinds of things. It's like you need some input from Earth, from the outside world, if you're trying to deal with that domain. And in the case of AI, where it's playing itself in a game, that's totally described, and it can move very quickly, where it just plays itself really, really fast. But in a case where you need, for self-driving cars, you need to actually go around and drive a lot and gather that information. So it's a huge amount of data, and then you can kind of match on that. And for many other things, it's too slow for feedback to run the experiment. So building a jet engine and putting it in a wind turbine is an example. Every time you do that, it's very inefficient to get the feedback. It takes a month to build what you need and see the result. So you only get a certain number of tries. In order for AI to be effective, you need to be able to have thousands, millions of tries, and those are only available in small domains where the computer can make legible the world around it. And that's where we're ending up with our problems in the world.
So it's a constrained environment. I personally don't think there will ever be autonomous cars driving around cities, because you'll get them at airports and you'll have them on freeways, because that's a constrained environment where humans aren't permitted. And so where they can keep everything in a restricted domain and predictable domain, then, because it's kind of like some version of a railway track. So you'll have, since the 80s, they had in Docklands Light Rail, they had trains without drivers. But that's because they were on rails, and it's a very constrained system. So you can have, a Tesla on a freeway, and it can do kind of a driverless train thing, but they're not really getting ahead with autonomous vehicles. It's the same shit as the 80s. They're just pretending and bullshitting everybody. But they're not getting any further ahead on what it's like on a street, where you can have, just the shape of leaves or something which look like a traffic light or a person crossing, or and it's just too unpredictable in that chaotic environment, where humans don't struggle in that environment because they have no because they're doing something fundamentally different. If a dinosaur jumped out, you would be able to swerve around it, whereas an autonomous car might go, oh, dinosaur wasn't in my training set, bang. It's that kind of stupidity.
I heard a good example of that, where I had a friend.
You want to say the last
Mercedes.
and then we put around it.
Oh, sorry. Just a quick one. I just had a good example of that, where a friend worked for Mercedes-Benz, and he said that they were really struggling with the English roads. Because they're old roads, and the AI, that works fine for autonomous cars on motorways. Lane changing and exiting the motorway. But on the English country roads, it's really old lanes, and they can't deal with with all the sort of foliage and the ins and outs of these tiny little B roads. They just can't deal with it. They're really struggling with that.
Well, this comes back to the general bigger discussion about the dangers of AI, and the biggest danger is that because AI's environment needs to be constrained, is they will make us serve the machines rather than have the machines serve us. So that's where it all lands, is that because they only work in a constrained environment, they will make us fit the one-size-fits-all constrained environment offered by AI, while telling us, oh, AI is going to do everything for everybody. And it's, no, we're going to become slaves to the fucking machine. We always were. Right from 10,000 years ago, they warned everybody that machines make slaves out of you. They never serve you. So that's the biggest problem about AI, is everybody thinks they're making, domestic robots to serve them, and they're not. We've been turned into slaves to serve this big Moloch machine.
That's
All right, we better end this.
let's end
Happy
it.
Halloween.
Okay, let's just pause and just let everything go. See the phosphenes behind your eyes, and maybe next time that's what I wanted to talk about is DMT and psychedelics, hallucinations, stuff like that. If AI can't do that kind of stuff, why can't it? And what's the human brain doing with psychedelics that's fundamentally different to a machine? So maybe that's the next installment. But you can see straight away by looking behind your eyelids, if you look long enough. I think some people said they couldn't see any lights or phosphenes or anything. It's because you are not in the right state. You haven't got to like the beta levels in your brain where things are really slowing down and you becoming relaxed, you concentrating, you watching the phosphenes feeding back and creating more phosphenes the more you watch. It's that feedback loop, and in those phosphenes in your eyes you can see fractal patterns, and those kind of get expressed with hallucinogens and entheogens, psychedelics. But you have them for free. You don't need to pay anybody or use illegal drugs. They're just right there in your brain. Rest in those. And observe your own intelligence in those patterns. The eye seeing the eye. Om Paramatmane Namah. Iti. Well, I hope that wasn't too boring for people. I really enjoyed talking to Ryan about it and people, but was it too slow for people?
No, thank you. Thank you very much.
Yeah, I'll review it. It's a lot.
Yeah, sorry if we use jargon a bit, but if there's anything that you want us to go over in more detail and de-jargonize it, we'll try.
It's like going to science grad
All
school.
right, everyone. Yeah.
Apologies on that.
Interesting ideas, though, that we're exploring.
Yeah, do
Yes,
stop us.
Thank you.
It is interesting.
Yeah. We'll try to use less jargon.
Yeah.
But if
Or just
if
explain it, just when
yeah.
it comes up. Just be sure to explain it.
Yeah, good idea.
All right, everyone. Well, happy Halloween.
All right.
Don't get run over by autonomous vehicles.
Ha 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 ha.
Lovely.
Bye.
Until next time.
Bye.
Bye. Yeah.